Hello, this is Professor Khan, and this week we are discussing chapter 3, and we'll take 2 weeks discussing this chapter because I believe it's very important. And we will do also some uh, we'll do some practice problems as well and see how it goes from there. Let me put on my headset. Okay, so this chapter will explain the concepts of basic electric circuit. What are the bases for making a circuit? Explain the characteristics of series circuit and also explain the characteristics of parallel circuit. And we'll discuss how series circuits are used in control and why do we need to do that. Okay, so move on. So again, our objectives: we calculate the current, resistance, and electro forces, which is voltage, in series circuit, and do the same thing for parallel. And the main thing that I would like you to remember is how to recognize a series circuit from a parallel circuit. Some of the terms we'll talk about: closed circuit, control circuit, electric circuit, open circuit, parallel, power circuit, series, combination, which is series parallel circuit, and also voltage drop. So usually when you have any kind of electrical circuit, it's a combination between a parallel and series circuit. It's never only one type, so you can have both. And the parallel circuit has more than one path. Okay, let me just illustrate here quickly. If this is my voltage source and this is the path, for series circuit there's only one path for the current to go through. If we go to parallel circuit, we have more than one path. And we have a load here, and what happens is the current going through here will stay the same here, then it will divide into more than one path. So this is the main thing that you need to know about how to distinguish between a parallel and series circuit. So, and why do we need both? Why do we need the series circuit in comparison to parallel circuit? We'll explain that shortly. So again, for any electric circuit, you need a complete path. Otherwise, there is no circuit. It's cut off, it's short, it's open. So you need a complete path for that to connect between the voltage and the loads. Closed circuit is when we have a complete path. If this is my source and this is my load here, we need to have a complete path. If there's a cut in here or breakage, it's not going to work. So that's an open circuit. The path is interrupted. A short circuit is different in that there is a path, but it's not the correct path. So it might go to a breakage, might go to another circuit here, or a ground. And also you can describe that when you have a short circuit. For example, when you have a parallel circuit and one of the paths is broke. So there is a path, but it's not the correct path for the current. So we are following the current, which is the flow of electricity in a circuit. So the electric circuit must have a complete path. We discussed that. A source of electron flow, which is a power source. It could be a battery, it could be alternating current, it could be an alternator, a generator, but we need the source for power. And we need the load, otherwise what is the point of the circuit? There must be a load, could be a light bulb, could be a motor, could be a control, so there is a load. So three things, which is voltage, source, then we have current, which is flow, and path. Current needs a path. And we have load, which is resistance, something that is useful to us. Load is the resistance, and that's why we are using this source. Think also about the water circuit in your house. If you have no faucets, there's no loads, there is no use of that circuit. This is an electric circuit. We have our plug over here, and this is my load, and this is the path. So this is a complete circuit right here, and you will get some use out of this load. If we break, even if this is the hot and this is the neutral, if we cut off the neutral, we're not going to have a complete circuit. The circuit is not going to work. So a series circuit is the simplest and easiest electric circuit. There's only one path for the current to take. So this is very useful for switches and control, meaning if we break that switch, the entire system will go down, and also good for control because it will turn on or off the circuit. So series circuit is good for two things: switches and control, also for safety devices. So if you have a fuse, it's good to put the fuse in the main path so it will cut off the entire circuit. And we did that in the lab when we wired one light bulb with the hotline, and we saw that all the switches and control devices are put in the hotline and not in the neutral, and if the neutral is not connected, the system is not going to work. So series circuits is done for switches and controls, and also it's used for safety. So do not connect safety devices in parallel. I'll give you an example. If we have a parallel circuit here, this is the source, and this go back to become one. If we put fuse in here, and this fuse goes out, the system still have power, so there is no use for that fuse. So we should put the fuse here in the main source of the power. So it should be in series with the circuit, not in parallel with the other loads. Okay, this is an example of a series circuit where we see the hotline here is going through three switches: high pressure, low pressure, and thermostat, then going to the motor. If any of those switches goes out, the circuit is incomplete, and thereby there is no flow, and the motor is saved. Okay. Characteristics when we do the calculation for series circuit is very simple. The current flow in one direction, so the current will stay the same in the entire circuit, meaning the current, if I go back here, the current is going through here is the same as the current go here, same in here, and also same in here. Current stay the same. And what happened to the resistance? They add up. If I have three resistances, and this is the current going through them, this is R1, R2, and R3. The total resistance of the system is going to be the sum of all those three resistances. Make sense? Okay. So, and what happens to the voltage? You will see that when we do the lab that the voltage will keep dropping. So the voltage here, for example, if we have the voltage source here is 120, the voltage here will be 120, then it will be consumed a little bit, so we might get here 80, and it will this resistance will consume some, and it will go to the third resistance, which will consume some, and at the end the voltage will be consumed completely throughout the circuit. And you will see if you put three light bulbs in series, the first one will be bright, then it will get dimmer and dimmer, so voltage will drop. Same thing if you have a big pipe with a lot of flow of water and three faucets in series. The first one will have a lot of flow, second one will have semi-flow, and third one might not have anything at all if the other two are open. Okay. Moving on, the voltage will be the sum of the voltage of the entire circuit, so the voltage will drop, which makes sense because if you have a lot of pressure, the first one will get all the pressure, then it keeps dropping. So just to repeat, what happens to the current will stay the same, voltage will drop, and resistance will add up. Okay. And we will also examine Ohm's law and how does it function in this kind of circuit. Parallel circuit. Again, we said there's more than one path for the flow to take. So there's a divide, there's a fork, there's a turn. The circuit does not have only one path, more than one path. It's very common. And you might think, why is that? Because if you noticed before, the voltage did drop in the series circuit, so it's really difficult to connect load with the same voltage. So most loads operate in line voltage, so all light bulbs with 100 wants to have 120 volts. If we connect the resistances in series, only the first one will get 120, then it will keep dropping and it's not going to function correctly. That's why it's very important to connect these loads in series. So if you have light bulbs, you want to connect those 3 light bulbs in this is light bulb, and a light bulb. You want to connect them in parallel, because now this one will have 120, this one will have 120, and this will have 120. So you want to connect loads in parallel, and you want to connect safety switches and controls in series. Okay, these are 3 loads connected in parallel. We can tell they are in parallel because this is line voltage, and if you notice the line coming from here, and it will divide. So we'll have here C1 is going to be C2 and C3. The C2 will divide further into C4 and C5, and here we'll have C6 and C7 and so on. So all of these currents will divide, but the voltage across the line 1 and line 2 and neutral will be always 120. So they will give the same voltage, but they have different currents. The current will be drawn based on the load itself. Again, I go back to the water flow example. If you have 4 faucets connected in parallel, if you open one faucet completely full, the other one will still be able to be completely full. If you open one that's small, it will take the flow it needs based on the opening of that faucet, and so on. So they have the same pressure, which is the same voltage here, but different current, which is different flow based on the load. So that's a good analogy to compare water flow with the circuit flow as well. So parallel circuit, this is simple AC schematics, and if you look here, we start from the line voltage, line 1 and line 2, and if we look in here, we see this is the contactor, compressor and fan, and they are connected in parallel because the current is divided to each one of them, and it goes back to the contactor here, and we have safety switches and control switches connected in series with this contactor, which is connects to here and here. The contactor is connected to both to open up the current. And what about this one? This is the heater. So the heater is connected in parallel, if you notice, with this circuit over here, and has the same control as well. So if you want to recognize on the schematic if the circuit is in series or parallel, you just have to follow the current. Just follow with your finger, see where it goes, and once it divides, you know those two are in parallel, not in series. So parallel circuit has different characteristics, and we said they have the same voltage. The current will be depending on the load, and so I'll say voltage the same. That's for the parallel circuit only, not the entire combination circuit. For the parallel circuit, current will divide based on the need, and resistance, what happened? This is the tricky part. It decreases. The resistance will decrease, which is good for us. We want to consume less because we have less resistance. So in series circuit, we said that the resistance will increase. In parallel circuit, the resistance will decrease. Try to wrap your mind around this. It's very important, and visual schematics also helps. So let's look at it. So the amperage draw, we said it will divide, so the total amperage will be the sum of all the little currents inside the circuit, and the voltage will remain the same, and the resistance will reduce. This is the math included in how to know what is the resistance. So the resistance gets smaller as more resistance get added up. So that's just kind of work to our advantage, right? This is the formula for two resistances, which is to get the total resistance of two resistances in parallel. So the addition gets a little bit complicated. So I came up with this idea I called FDAF, and how to calculate the total resistance of few resistances in series. So I will start with R total equal R1 plus R2 plus R3, and I flip. By flipping I mean you divide 1 by the value, then you divide. So I did the flipping, you divide, so you get a number, so you have to transform from fraction to decimal, which make things a little bit easier. Then you add the total numbers, you get a total number over here, and you still maintain the equation the same way it is, 1 over RT. Then you finally flip again, which is dividing 1 over the number you got from here. I have a worked example to make things a little bit clearer. So let's imagine we have this circuit. I'm gonna draw it over here. Here's R1, R2, and R3, and they connect again together and go back to here, the circuit. So these three are in parallel because we see that there's a divide in here. And how do I get the value for this entire parallel circuit? So I'll start with R total equal R1 plus R2 plus R3. Okay, first thing I do is I flip. So I divide 1 over RT, which I don't have, 1 over R1, 1 over R3, and so on. Okay, so I got that in here. Flip, divide. So 1 over R1, R1 is 2, I put 1 over 2. R2 is 5, so 1 over 5. And R3 is 4, so 1 over 4. So this is the first step, I divide. You get a number. So we change from fraction to decimal. That looks much easier to calculate. Maintain 1 over RT. It's just going to transfer the way it is. Then I'm going to add the total, which is the sum of those three. And I still have 1 over RT. And finally, RT will be 1 over that number, which is 1.052. Okay, two things I want you to remember. The first thing is that do not forget to do the last step. People leave this and say, okay, this is my R total. No, this is 1 over your R total. So you have to divide 1 over that to get the right amount of ohms. The second thing is the total resistance should be smaller than the smallest resistance in that parallel circuit. So if you notice here, it's 2, 5, and 4, and 1.052 is smaller than any of them. If you get a number larger than those, you did something wrong in the calculation. And this will require some practice. If you do a few of them, you will manage to see and how it's done. And once you get the process done, please try to be organized. And this step I find is the easiest one. If you have different app or like mean to do it, that's fine. If you have different mathematics to do it, that's fine. But I find this is the most easier and clearer way to do it, at least for me and for people who tried it. So I posted some few examples on Blackboard regarding how to do these. So get to practice, and they have a solution in it. You need to practice these a little bit by hand because it will make it a little bit clearer, and you'll have a sense of how the math goes. Okay, so again, in parallel circuit, we said the voltage drop, there is no voltage drop. It will be the same, so always you will have the same voltage applied in that parallel circuit to each load. Okay, so series and parallel circuit, it's a combination, so they are common in all controls, so you'll see both. What I need you to know is you have to distinguish between resistances in series and parallel. So if I have this circuit, this is a combination circuit now. So this resistance and this resistance are in series. These three resistances are in parallel. But this parallel circuit here is in series with these two. So the first thing you do is you find the total resistance for this circuit, then you add it in series with those two. So visually, it's important to understand how they differ. Okay, here's another schematic for a combination circuit, and you see those two are in parallel. What about these? Series. What about this and this circuit? They are in parallel. What about this and this circuit? They are in parallel. This circuit here and this circuit, and these are all in parallel. So there is a large circuit and there are sub circuits, and you'll get to wire some of those loads together in the lab, and you see how does it make a difference. And it's very important to connect things in series and parallel as they are in the schematics, otherwise you might have a problem of the equipment not running correctly. Okay, applications. So most ACs or boilers or furnaces, you will have both. You will have series circuit and you have combination circuits as well. So we just need to recognize them from the schematic and see how they are connected. And if you just keep in mind that things, that switches and controls and safety switches are always in series, and that loads usually are done in parallel, you will start to recognize these clearer. And you'll do some wiring for ACs and also for boilers in the lab, so hopefully this will make things a little bit clearer. Another example of a combination circuit. This looks a little bit overwhelming, but it's not. What do you do when you see this kind of schematics? Look at the source. We start from the line voltage. This is what you plug into the wall, and we go from there. And usually there's something called a legend here that tells you what are those components. This here is a transformer. Usually this is the main equipment, and this is the control. So the control usually is low voltage, around 24 volts, and the main circuit is the actual working equipment. So the control is always low voltage, and you can see it's a combination between series and circuit. We'll spend the whole chapter talking about schematics and how do we read them. Okay, so I would love for you to look at the book, chapter 3, and I will spend next week trying to solve these some problems and examples that I put in the blackboard and answer some questions, and I will do one live problem with you here in the board so you can see and can ask questions as we go along. And if you can focus in recognizing a series and parallel circuit, you have done a great job. Again, I will post this video and I'll post some problems for you to practice on. And next week we'll do some few practice problems just to make sure that you got this right. Okay, thank you very much.